Today's lesson is the final day of data analysis. This is day 3. The sequence below shows the raffle tickets that Samantha sold each day during a month. She sold 3, then 7, then 11, and then 15. Which explicit formula models the number of tickets Samantha sold on day X? Well, it's not super obvious, but this is an L1, L2 kind of problem in your calculator. So it's the number of tickets that she sold each day during a month. So day 1, she sold 3 tickets. Day 2, she sold 11 tickets. Or she sold 7. Day 3, she sold 11 tickets. And day 4, she sold 15. So this is what I'm going to take to my calculator when I type this data in. So I'm going 1, 2, 3, 4 for my days, and then 3, 7, 11, 15 for my tickets. Get my equation. So it's y equals 4x minus 1, which is C. Number 2. It says there were originally 4 trees in an orchard. Each year, the owner planted the same number of trees. In the 29th year, there were 178 trees in the orchard. Which function, T of n, can be used to determine the number of trees in the orchard at any given year? So this should remind you of the car problem when you were trying to figure out how much it was depreciating each year. So we're going to write points. So originally is 0. We had 4 trees. So when we started, we had 4 trees. Originally does not mean 1. It means go all the way back to your y intercept, which would be 0. And then in the 29th year, we have 178 trees. I think it's very beneficial to write your points and to write them stacked on top of each other. That way you can kind of see these are your L1s and these are your L2s. So just a little trick of the trade if you want it. So then I go to stat, edit, clear these out. I have a 0 and a 29 and a 4 and a 178. And I get y equals 6x plus 4. So that's going to be C. Then another problem very similar. There are 10 bushes in Mitchell's nursery. Each year the Mitchells planted the same number of bushes. In the 18th year there were 280 bushes. Which function B of n can be used to determine the number of bushes in the nursery in any particular year? So originally there were 10, and in the 18th year there were 280. You're going to go to your calculator, you're going to L1, L2 it, type it in, and get your equation, and you're going to get y equals 15x plus 10, which is A. Again, feel free to take your time and go practice that on your calculator. Pause the video and practice that to make sure you can get the right equation. Number 4, the table below shows the cost of a pizza based on the number of toppings. So obviously as the number of toppings increase, the cost of the pizza is going to increase. And it says which function represents the cost of a pizza with n toppings. So not a problem. We go L1, L2, and we type this in, and we get y equals 1.5x plus 10.5. So that's my equation. And then I go look at my 4 choices, and I don't see it. And the number one mistake students make is they're going to pick B because it has the right slope and the y-intercept is really close, but it's not the same. B's y-intercept says that a pizza with 0 toppings on it is going to cost $12, and our equation says a pizza with 0 toppings is going to cost $10.50. Well, that's a big difference. So this is when they take a problem that's very straightforward and very easy and try to crank it up a little bit and make you work a little bit harder for it. If you'll look at A, you can see it's kind of a crazy equation. It's not cleaned up. So what we're going to do is we're going to take A and we're going to clean them up. So I'm going to bring down my 12. I'm going to distribute my 1.5. And then I'm going to combine my like terms. This doesn't involve adding or subtracting anything to the other side because I'm still all on the right-hand side of the equals. I'm going to pull that up front, and then I have this term, and if I do 12 minus 1.5, it gives me 10.5, which is exactly what my equation was in my calculator. So the answer is A. It was just hidden in all of the fluffiness of that answer. So you have to get through all the fluffiness, straighten it out. You've got to distribute, you've got to combine your like terms, you've got to clean them up and look at him. You can't tell what he is when he's all messed up like that. Number 5, the sequence below shows the total number of days that Katrina went swimming by the end of weeks 1, 2, 3, 4 of her new workout routine, and they were 3, 5, 7, 9. Which function can be used to find the total number of days Katrina swims at the end of the week X if her pattern continues? Well, this is just like day 2 of data analysis. You're going to L1, L2, so L1 is going to be your 1, 2, 3, 4, and L2 is going to be your 3, 5, 7, 9. And we can do that, not a problem. That's going to give us y equals 2x plus 1, which is great, easy, not a problem. And then we got to look at our answers, and it's not this guy. It's not that guy. And I have no idea if it's C or D because I have to clean them up. So let's take C. And let's distribute. So that would be 2x plus 2 minus 3, which would be 2x minus 1, which is not what I want. So let's try D. Bring your 5 down. Distribute your 2. Bring your 2x. And then 5 minus 4 is a positive 1, and that is exactly what I want. So there he is. He was just hiding a little bit. Got to mess with him. And then we can match it to our answer. A set of data is shown in the table below. It says, assuming it's a linear relationship, what is the predicted value of y when x is 4? This is the word you need to focus on. If you think about a scatter plot and your line that goes through, everything that's on this line is a predicted value. All of these dots are actual observed values. This is what actually happened. So what I want to know is when x is 4, what are we predicted to be? So the first thing I need to do is get the equation of my line. Well, to get that, I just L1, L2. So I type this information into my calculator, and I got y equals 2.95x plus 9.59. And I always find that it's really good to go 2 decimal places and just really watch your rounding. So that's the equation. Well, wants to know what is the predicted value when x is 4. Well, when x is 4, so that means I take a 4 and I plug it into my x value. So I take my calculator and I do 2.95 times 4 plus 9.59. So I'm plugging a 4 into my equation. And I get 21.39. So we're going with 21.4. So you can use your prediction equation to find predicted values. Just take your x value and plug it in for x. The table below shows the average attendance at a football team's games in different years. So in the year 2000, they had 7,650 kids come to the game, but in 06, they're up to 13,000. So it says, assuming a linear trend, in what year was the team's attendance first predicted to be greater than 20,000? So let's pretend that the athletic director says, hey, I'll build you a new stadium if you can pull in 20,000 people. And so the coach wants to know, well, at this rate, at what year am I going to get this new stadium? Okay, so the kicker here is to remember that these are X's and these are Y's. Well, what is he? 20,000 is a population. He is an attendance. So this is actually a Y value. So yes, I'm going to L1, L2, I'm going to get my equation, but you've got to make sure that you understand that you're not plugging in a 20,000 into this problem like we did the last one with the 4. You L1, L2, and these numbers are huge. 863.25x minus 18628. So there's my equation, and that's from going L1, L2 on my calculator. Feel free to pause the video and punch those numbers in to make sure you can get that equation. So 20,000, like we said, is a Y value. These years are my X's. And I want to know the year it first reaches 20,000. So I'm going to take my calculator and I'm going to type my equation in and I'm going to plug in my first year. What's my first year? 2010. So what am I looking for? How do I know if this is my answer or not? Well, in 2010, we've got 16,504 people. So we have not reached 20,000 yet. So I need to keep plugging in. So B is 2013. Now there's a nice little trick you can do to not have to retype this formula in. If you look at your enter button above it in blue, it says entry. So if I go second entry, it pulls up the last thing I typed in, and I can go under this 2010 and change that to a 3 and hit enter. So now I've got 19,094 people. I still haven't hit 20,000 yet. So let's see if it happens on 2015. So second entry, I just want to change that to a 5. And bingo, we've hit 20,000. So I'm going for C. Now some students will say, well, I started with 2017. If you plug 2017 in, you're going to get something that's over to 20,000 people. But if you read the question, it says, in what year was the team's attendance first predicted to be greater than 20,000? And so that wants not just a year that it's bigger than 20,000, but it wants the year that it first goes over 20,000. Number 8, the table shows the number of hours spent studying and the exam grade they earned. So how many hours they studied and what their exam grade was. Use a linear model to approximately how many hours would a student study to earn a 97. So let's say you're grounded and your mom says you can't be ungrounded until you make a 97. So you want to know how long you've got to study to get that grade. So what I'm going to do is I'm going to type this in to my L1, L2, and I'm going to get my equation. And again, feel free to practice that, but to save us some time, I've already found it. So there's our equation. Now I want to earn a 97. So the question is that an X or a Y? Well, that's a grade, so that's a Y value. So what I want to do is plug these in and find me the one that will get me a 97. So I'm going to take my calculator, clear this out. I'm going to go 8.2 times, let's see, 3 hours is our first one, plus 68.7. And that gives me 93.3. So we haven't hit our 97 yet. So now I'm going to go second entry. And let's plug in a 3.5. Okay, so now if I plug in a 0.5 right here, it's going to type over the plus and the 6. But if you look to the left of your arrow buttons in blue, it's your delete button. Above it, it says INS, and that stands for insert. So I'm going to second insert a decimal. And you see how it slid everything over? And then I'm going to second insert a 5. And it took my plus sign anyway. There's my plus sign. Okay, so then I hit enter, and that gives me 97.4, and that's what I wanted. I wanted a 97, so it's going to take me 3.5 hours of studying for me to get my 97. All right, this one is really great, especially for reading things really carefully. The table below shows the number of hours Tammy worked during 5 days and the amount of tips she earned. So one day she worked 6 hours and she made $71 in tips. But then if you'll look down here, here's another day she worked 6 hours and she only made $55 in tips. So this is real data. This is observed data, what actually happened. I want the difference, so I'm going to subtract something, between the observed and the predicted at x equals 7. So when she worked 7 hours, how much did she actually make minus how much we would have predicted her to make. So we want to see if it was a good night or an off night. Okay, so the first thing I'm going to do is I'm going to write observed minus predicted. When x equals 7, I can see my data right here. So when she worked 7 hours, she made $90. And again, this is observed data. So that 90 is my observed. To get my predicted amount at 7 hours, I need to find my equation. So I type my data into L1, L2, and I get my equation. And it's 15.59x minus 31.86. So that's my equation. That's my prediction equation. So now I want to know what this equation predicts for her to make at 7 hours. So I'm going to plug a 7 right there. So I'm going to take my calculator and I'm going to do 15.59 times 7 minus 31.86. And I got 77.27. So that is her predicted. So can you tell me, does she have a good night or a bad night? And actually, she had a great night because she made $90 and she was only predicted to make $77.27. Well, I want the difference between these two. So I'm going to take my 90, which was my observed from the chart, minus my 77.27, which is my predicted from my equation, and I got 12.73. So she actually made $12.73 more than she was predicted to make. If that number had come out to be negative, then she would have had an off night. She wouldn't have done as well as she predicted. Maybe she was grumpy and didn't earn a good tips, or maybe the restaurant was really slow, or maybe, I don't know, maybe she dropped some food on somebody and she didn't get a good tip. But because it's positive, her observed is higher than her predicted, so she actually made more than she was predicted to make. Number 10, the table below shows the charge for different number of shirts from an online website. The company charges a cost per shirt and a setup fee per order. What is the difference between the observed and the predicted? Okay, so difference, observed, predicted, 150 shirts. So 150 shirts is right here. Observed minus predicted. Observed is $354, and I'm getting that from my chart. For 150 shirts, it is observed that it will cost $354. To get my predicted, I need my prediction equation. So I type all this in to my L1, L2, and I get this. So then I take my calculator, and I take my equation, and I'm going to times it by how many shirts? 150. And hit enter. And I got 348.9. And then to figure out what the difference is, I'm going to do 354 minus 348.9. And I got 5.1. So it's a difference of 5.1. So again, observed is from the chart, predicted is from your prediction equation, and then you just subtract. The table below shows the shirt size and the age of 6 girls. So if we look at our table, it's got shirt size. So this girl wears a 3T, and she is 3 years old. This girl wears a 3T, and she is 4 years old. She wears a 4T and she's 4. She wears a 5T and she is 3. So you can see what kind of information we've got here. This is approximately what percent of the girls' ages is more than 1 year different from the age predicted by the line of best fit. Okay, so the first thing I need to do is find my line of best fit. So L1, L2, all this information, and I get Y to be 0.24x plus 2.83. So that's my prediction equation. And again, I want to remind you that these are x's and these are y's. This is all observed data. I need to find its predicted data. based on the shirt size. So I'm going to take these x's, all of these x's, and I'm going to plug them into my prediction equation to get my predicted y's. Okay, so let's take my equation, and I'm going to go 0.24 times. All right, and my first shirt size is a 3. Now, again, I'm on the x's. I'm not looking at the ages. I'm looking at the shirt size. So their shirt size is a 3. And I got 3.55. So again, I plugged in this 3 and I got 3.55, and I'm comparing it to this 3 in just a minute. Now, to plug in this 3, I'm going to get 3.55 again, so there's no need to do that again. To test the 4, I'm going to go second entry, come back over here, type in a 4, and I got 3.79. Okay, and now I need to type in a 5, and I think this is the last one I have to do. And I got 4.03. Because those are all 5s. So now I want to find what is more than a year difference. So what I'm looking at now is I'm comparing these to these. These are my observed, and these are my predicted. So I want to know which ones are more than a year difference. So what is the difference between a 3 and a 3.55? And it's only 0.55, so it's not more than a year difference. Okay, a 4 and a 3.55 is not more than a year difference. A 4 and a 3.79 is more than a year difference. And if you're having trouble seeing this, all you have to do is subtract the two numbers. So 4 minus 3.79 is not more than a year difference because it's only 0.21. I need it to be bigger than 1. Okay, now compare a 3 to a 4.03. Yes, that is more than a year difference. Let me show you. So 4.03 minus 3, or you could do 3 minus 4.03. It doesn't matter. The point is that it's bigger than 1. It doesn't matter if it's positive or negative. So he is bigger than 1, so this is one of mine that works, that is more than 1 year difference. Okay, now compare the 4 to the 4.03, and that's not more than 1 year difference. The 5 and the 4.03 is close, but it's not more than a year. It's only 0.97. So how many do we have that are more than a year difference? And the answer is 1. So we have 1 that's more than a year difference. Out of how many total kids? We had 6 kids. So to figure out what percent that was, because that's what it's asking for, I'm going to do 1 divided by 6. And I've got 17%. Okay, the table below shows the pant size and age of 5 boys. Approximately what percent of the boys' ages is more than 1 year different? So the first thing I need is my prediction equation. And this one's really nice and tidy. Okay, and so again, reminder, these are x's and these are y's. So I'm going to plug in all my x's and get my prediction. So I'm plugging in all of these into this formula and getting my y's. So I plug in a 3 and I get a 3. I plug in a 4, I get a 3.8. I plug in a 5, I get a 4.6. I plug in a 6 and I get a 5.4, and I plug in a 7 and I get a 6.2. And that's just plugging them into this formula. Feel free to pause this, plug those in to make sure you see where those numbers are coming from. So I need the one that has more than a year difference. So that definitely does not. Those are dead on it. This is only going to be a difference of 0.8. Now 6 and a 4.6, the difference here is more than a year. So he's one of mine that works. 5 and a 5.4 is not more than a year, and a 6 and a 6.2 is not more than a year. So I have 1 again that works, but this time it's only out of 5 kids. So to figure out the percentage, I just do 1 divided by 5, which would give me 20%. So the answer is A. Okay, so these are involved problems, but they're not difficult. So take your time, read, make sure you understand the difference between observed and predicted. As observed comes from your table and predicted comes from your equation. So take your time to figure these out and feel free to pause or replay as often as you need.